This is video lecture 8.75. So now getting back to our categories of research design that we started looking at before, the next experimental design to talk about is this one, true experiments. So this is probably what most of us think of when we think of a scientific experiment. So in a true experiment, a researcher is going to be comparing the effects of, say, a particular treatment with that of a different treatment, and that would be the experimental group, or of no treatment at all, the control group. And the experimental group or groups are going to be exposed to some influence, some treatment, something that the researcher is interested in, and of course the control group is not. So the defining characteristic of a true experiment to make it a quality experiment is going to be random assignment. So any one subject has to have the same probability as any other subject of getting into one of the study groups, say an experimental group versus a control group. So it's interesting though, you have to distinguish here between random assignment of subjects to the various groups in a true experiment. And don't confuse that with the random sampling of people from a population to even be subjects in your experiment in the first place, right? So really, for a successful, fully generalizable true experiment, you have to maximize both random sampling from your population to get your group of study subjects, and then practice good random assignment to groups. You have to get both of those things right. You might take a good random sample of people for your study, but then let them choose the group they want to be in, or assign all randomly sampled males to one group and all females to another group. Now you don't have a quality true experimental design anymore. So going back to our jury size example, let's say we have a hypothesis that a 6-person jury or 6-person juries in general award larger damage amounts in civil cases than 12-person juries. And our hypothesis further suggests that maybe because they're smaller samples, they're less likely to be representative of the population and more volatile, for example, as a result of that. We might then write up a civil trial scenario, right, and then test that scenario with mock jury panels. Despite the cartoon here, we're probably going to be using college psychology students and not lab rats to be our mock jurors. So in designing an experiment to test this 6 versus 12 juror hypothesis, maybe we could set up 15 mock jury panels of 6. That would take 90 subjects, right? And 15 mock jury panels of 12, that would take 180 subjects. So we would need 270 research mock jurors here, and we'd be randomly assigning them to their respective groups. Then we'd give them the case materials to consider and deliberate on, and then later we could compare whatever it was we asked them to do. We could compare their verdicts, we could compare damages awarded, we could also look at other things like deliberation time, how long did the jurors deliberate on average. We could look at the participant satisfaction with the process, whatever additional outcome variables we might be interested in as scientists. Now, in this true experiment, like I said, we might only be using college sophomore psychology majors who are certainly self-selecting to be in our original sample before they get randomized. So we can't say we've randomly sampled a population like the ideal situation where actual juries are chosen from voter rolls. But still, this kind of experiment is going to have high internal validity, right, due to the careful random assignment of our subjects to groups. But here, external validity might be a problem. For a lot of purposes, the true experiment is the ideal research design because it eliminates a lot of those plausible rival hypotheses that make deriving a cause and effect relationship difficult. Randomized assignment, at least in theory, and usually in practice, does control for all or most of those common threats to internal validity we talked about, except mortality, right? Because of course, more subjects might end up randomly dropping out of one group than another. And that would make our results more difficult to interpret. Also, we should note one more thing from the other slide, and that is you can randomize by different units of analysis, like in the prison study example in the book. So you could randomly assign prisons to different programs if you find prisons that fairly closely match each other in terms of their demographics, or you could actually randomly assign prisoners within the same prison to your different programs. So there's different ways of setting up your experimental groups. Now the book does talk about the fact that if you randomize prisons instead of prisoners, you might have some additional confounding issues, like if the prisons are in different areas of the country, for example, and job prospects might be better in one area than another, so the prisoners might end up being released into different environments. So if you want to study their adjustment after prison release and you're releasing them into different environments, now that's a major confound that's going to affect the validity of your data. So a lot of factors are going to have to be considered when you as a scientist decide which unit to randomize. Okay, so sometimes it's just not possible to do a true experiment, right? Nobody wants to randomly assign murderers to the death penalty to see if their friends end up being deterred from committing violent crime. You're not going to randomly divide up babies in an orphanage and have one group exposed to a lot of nurturing and the other virtually ignored to see if those kids develop differently. You're not going to take a bunch of 18-year-old college students and randomly assign one group to smoke 2 packs of cigarettes a day for 40 years so that you can compare them with the non-smoking group to look at their heart disease and lung cancer rates, right? So here I want to talk about quasi-experiments. So a quasi-experiment is an empirical study used to estimate the causal impact of some intervention on a target population. Right? An empirical study used to estimate the causal impact of an intervention on a target population. Well, that sounds a lot like a true experiment or a randomized controlled trial, right? But the one thing that's missing is the element of a random assignment to the treatment group or the control group. So instead, in a sophisticated quasi-experimental design, the researcher does control which subject he or she puts into the control group and the treatment group. But instead of random assignment, there are going to be other criteria of assignment here with a quasi-experiment. So again, quasi-experiments have similar purposes, similar structural attributes to randomized experiments, but they lack that random assignment of units to conditions. And remember, the criteria for assignment are still selected by the researcher. And a lot of quasi-experiments are very carefully designed to try to minimize confounds. So when I use this phrase quasi-experiment here, I'm talking about, in many cases, very, very sophisticated studies. So there are a lot of definitions out there about defining quasi-experiments. Here's a definition straight out of the Cook and Campbell book. They literally wrote the book on quasi-experimental design. So here it is. Quasi-experiments have treatments, outcome measures and experimental units, but they don't use random assignment to create the comparisons from which treatment cause change is inferred. Instead, the comparisons depend on non-equivalent groups that differ from each other in many ways other than the presence of a treatment whose effects are being tested. The task confronting persons who try to interpret the results from quasi-experiments is basically one of separating the effects of a treatment from any effects just due to the initial non-comparability between the average units in each treatment group, right? Because only the effects of the treatment are of research interest. That was the simple official definition I could find. Okay, so when I talk about a quasi-experiment, this is going to be an experiment that's basically constructed in the real world and constructed in real time. Okay, and even though the researcher is going to try to make the groups as identical as possible on any characteristics she can, quasi-experiments are always going to be vulnerable to internal validity problems because the treatment and control group might not be comparable enough at baseline. So I have a couple of examples here. If you wanted to study alternative dispute resolution frameworks, a lot of mediation evaluation projects, for example, depend on quasi-experimental designs, right? They just look at outcomes of mediation. They look at satisfaction ratings by participants in mediation programs compared with people that are engaged in similar disputes who don't do mediation. But of course, since participation in mediation is voluntary, right? You start out right out of the gate with potentially skewed samples. Certainly, it's really easy to imagine that people who choose to try mediation might differ on any number of characteristics from people who don't choose that. And an example in the medical context, I have on the slide an example of trying to study alcohol use in pregnancy and its effect on babies. Again, you're not going to randomly assign some pregnant women to drink a certain amount during pregnancy, but in a quasi-experimental design, maybe you'd collect data from women on how much they did drink during pregnancy. You'd assign them to your groups based on their answers, and then you would compare the groups based on amount of alcohol they consumed and look at the health outcomes for the babies. So the problem with quasi-experimental designs, obviously, is that a lot of variables are going to be difficult to control. So in our alcohol and pregnancy example, and in other medical causation examples where you're asking someone to self-report, that can run into obvious difficulties, right? You've got issues with, well, how much do the people actually remember? How honest are they being? And then, of course, there are other things that could be affecting, say, in your pregnancy and alcohol example, other things that might be affecting the baby's health outcome, like nutrition of the mother, the quality of prenatal care the mother got, or other background pre-existing characteristics of those moms just aside from their alcohol intake. So you can try to control for some of those things by also collecting data on all of these other factors and taking those into account when you assign your moms to your experimental groups or your control groups, or even eliminating people from your samples if they are just really big outliers in one of those other factors. And that is exactly what the most sophisticated and high quality quasi-experimental designs do. So you've probably heard the phrase matched controls at some point, matched controls. So a really diligent researcher with a quasi-experimental design is going to try to assign subjects to a control group that match each subject in the experimental group. So ideally in our pregnant mom study, if we had a 27-year-old Caucasian obese mom who drank the equivalent of 2 drinks a day while pregnant, we we would want for our control group a 27-year-old Caucasian obese mom who didn't drink, if we could get it. But you can see, though, how really difficult it would be to match subjects perfectly. So as a general matter, it's a lot more difficult to show a statistically significant cause and effect with a quasi-experiment. I have on this slide some of the quasi-experiment examples from the Monahan and Walker book. You know, some of these would be considered not very sophisticated quasi-experiments. So the before and after experimental designs, where you just take an individual or even a group, you subject them to something, and then you measure some variable. Like, for example, in television commercials on tooth whitening, you know, people use the tooth whitener, and then you measure how white their teeth are. Of course, they're going to be subject to maturation threats, history threats, not to mention being subject to other more nefarious threats like photoshopping by the company that sells the tooth whitener product. The next one, simple comparison group designs, they're certainly subject to the threat of selection biases. For example, if you have one group that volunteered for a program and another one didn't, right? If you just really are just simple about looking at your groups and you don't try to do any kind of matched controls. The next one, time series designs, kind of an interesting one. This is the design that measures the same group at more than 2 points in time. Some people consider these to be among the best of the quasi-experimental designs if you want to draw a cause and effect conclusion. But even in a fairly good time series design, that history threat is going to be a plausible rival hypothesis, right? Maybe some other event or effect rather than your variable of interest ended up causing the change in your dependent variable because it took place over time. But one of the reasons, though, these are considered better than some of the others for inferring causation is that you do have multiple measurements over time, plus you have the ability to look in hindsight and actually find some of the possible history effects that might have affected your results. At least certainly in some cases you can do that. The book gives this great example on page 88 and 89 of the reduction of the mental hospital population after the passage of the 1963 Community Mental Health Centers Act. So here we see how dramatically the mental hospital inpatient population increased from 1830 to 1955. And here we see how the population changed from 1955 to 2006. So the question was, did this 1963 Act have the effect of decreasing the mental hospital population? So the time series measurements that were done here actually showed that the passage of the Act did not appreciably accelerate the rate of reduction of population from the rate of decrease that had already started in the mid-1950s. And that reduction started in the mid-1950s because that is when the first antipsychotic medications were available. There was actually another possible confound in this situation too, because after the mid-1950s, mental hospital workers unionized, which vastly increased the cost of hospitalization to states. So in fact, states also started discharging patients at a higher rate to cut costs. So this is a great example of a time series design where if you're looking at the effect of this 1963 Community Mental Health Centers Act, you basically have to deal with these couple of major confounds that happen. But because you did a time series design, you're actually able to look back and see what those other threats were. Okay, we can go back to our jury study that we talked about where we had a true experimental design using those college sophomores, which we think is going to have pretty good internal validity, but maybe there were some problems with external validity, right? Or being able to generalize our results to actual juries. So in order to further test our hypothesis, maybe after we did that true experiment with our college students, we might decide to try to devise a quasi-experimental design also to augment those true experimental results. So for example, we might, as I show on this slide, compare state A that uses 6-person juries with state B that uses 12-person juries. I used this, in fact, as an example earlier when we were talking about internal validity problems, you might remember. So here, any differences between these two states on whatever outcomes we're measuring might be attributable to the types of cases coming to trial in each state, different litigation strategies among the lawyers, different traditions, different regions of the country. So if we did want to use this quasi-experimental design, we would try to minimize those if we could by finding two states that are similar as possible on all those other measures, but that differ only in their jury size requirements if we could. So another possible strategy might be to take advantage of a natural experiment. So let's imagine state C has just implemented 6-person jury panels after decades of 12-person jury panels. There, we might be able to study the records of this state and compare, say, civil jury awards before and after that change. So like I just said, this is referred to as a natural experiment, often thought of actually as a subcategory of a quasi-experiment. So natural experiments, just like it sounds, basically take advantage of some naturally occurring event of interest. So it's really just like an observational study where the assignment of treatments to subjects has been made by nature and not by experimenters. So like I say on the slide, they're most useful if you have some clearly defined and large change in some treatment or exposure to a clearly defined subpopulation so that any changes in responses can therefore be plausibly attributed to the change in treatment or change of exposure. So you get a lot of natural experiments in epidemiology, you get them in economics. So a couple of quick examples here, comparing tranquilizer sales in a community hit by a hurricane with sales in a similar community that wasn't affected by a hurricane. Or maybe comparing alcohol drinking levels at two colleges with similar student bodies, one having an orientation program about the dangers of alcohol abuse and alcohol poisoning, and the other not having such a program. Another good natural experiment, which we actually saw when states passed seatbelt laws, was looking at the number of accident fatalities in a state that passes a seatbelt law. So the difference between natural and quasi-experiments is that in a quasi-experiment, the criterion for assignment to groups is actually selected by the researcher. You know, for example, doing match controls or something like that. While in a natural experiment, both the assignment occurs naturally, right, without the researcher's intervention. So in fact, both of these experimental designs can be used to study the same phenomenon, which you often see in the epidemiological context. But I wanted to go over this really fascinating historical example of the power and benefit of natural experiments. And this happened during the cholera epidemic in London in 1854. So this guy here on the right of the slide is John Snow, a London doctor who's sometimes referred to as the father of epidemiology. He actually used two different natural experiments to help him come up with his hypothesis about what might cause cholera. So we know now that cholera is caused by a bacterium and that it's spread very easily when water gets contaminated with the fecal material of people who are sick with cholera, or sometimes people who aren't actively sick but who actually are carrying that cholera bacteria. So we know that cholera is a big risk whenever there's a natural disaster and fresh water supply systems break down. So back in London in the 1800s, there were two major cholera epidemics about 4 years apart, one in 1848 and 49, and the other one in 1853 and 1854. And it was during this later epidemic that John Snow paid very close attention to two natural experiments, and they helped him come up with the idea that something in the water supply was causing the disease. So this is really before microscopes were available, of course. So this wasn't a matter of, oh, why don't we just look at some water samples under a microscope and see if there's something in there. So he didn't have that. But what he did have were these two natural experiments. So the first observation John Snow made, the first natural experiment, was in South London. And in South London, interestingly enough, there were two competing water companies that supplied water directly into people's homes. So this was a middle class type neighborhood that actually had running water in their homes. And the main pipes from both of these two competing companies ran under some of the streets. So in some areas, it was really common for houses right next to each other to be getting their water from different companies through different pipes that came from different sources of water. One of the companies pulled their water from the Thames River downstream from a place where raw sewage was dumped in, and one company drew their water upstream from that sewage dumping. And this fact actually brought about a weird sort of randomization of a lot of other variables aside from water supply, right? Because there were different families living in these houses where our independent variable here was which water company they got their water from. But we would expect that the other factors would actually have been randomly, evenly distributed in these neighborhoods, right? As long as there was a big enough sample of households, right? Things like pre-existing health conditions or nutritional habits or family size. So not surprisingly to us, right, we who know what causes cholera, John Snow found that the households that were serviced by the company drawing that downstream water had about 10 times as many cholera deaths as the households served by the upstream company. So that was his first natural experimental finding. And the second natural experiment is certainly the more famous one. So this is John Snow's famous cholera map. What he did here is he mapped cholera cases in the Soho area of London. So this is a lower socioeconomic neighborhood, very densely populated. This had had a huge eruption of cholera cases. So he had his map, and what he did is he went house to house here, and you see these lines. He basically drew these lines in front of every address when he went and interviewed to show all the cholera cases in those households. Then he tried to figure out, well, what do these cholera households have in common? And what he did is he traced their water supply to a particular pump here on Broad Street. And this was a hand pump that brought up water from a shallow well. These were lower socioeconomic households that didn't have running water, so they had to get their water from pumps. The other piece of evidence that he gathered, excuse me, that supported his hypothesis was that people who lived over here in the workhouse and people who worked at the brewery, where is the brewery? Over here, okay, who got free beer to drink, they had hardly any cholera cases. And in fact, people who lived in the workhouse and people who worked at the brewery didn't use that Broad Street pump. So here is an actual direct quote from a letter to the editor that John Snow wrote to the Medical Times and Gazette of London. He says, "On proceeding to the spot, I found that nearly all the deaths had taken place within a short distance of the Broad Street pump. There were only 10 deaths in houses situated decidedly nearer to another street pump. And in 5 of those cases, the families of the deceased persons informed me that they always went to the pump on Broad Street as they preferred the water to that of the pumps that were nearer. In 3 other cases, the deceased were children who went to school near the pump in Broad Street. With regard to the deaths occurring in the locality belonging to the pump, there were 61 instances in which I was informed that the deceased persons used to drink the pump water from Broad Street, either constantly or occasionally. The result of the inquiry then is that there has been no particular outbreak or prevalence of cholera in this part of London except among the persons who were in the habit of drinking the water of the above-mentioned pump well. I had an interview with the Board of Guardians of St. James's Parish on the evening of September 7th and represented the above circumstances to them. In consequence of what I said, the handle of the pump was removed on the following day." So after this happened, more investigation actually was done. And what was discovered, a kind of a disgusting discovery, is that this shallow well that fed the Broad Street pump, it was dug just 3 feet from an old cesspit that had been leaking. So a cesspit is basically a pit that they dug back in the day under people's houses. They were kind of precursors to modern septic systems of today, these cesspits. But there was a baby who had had cholera whose diapers were being washed out in a cesspit that was very near the Broad Street pump well. And that actually was Snow's hypothesis of how the Broad Street well got contaminated. So his idea of the cause of cholera being some kind of living thing, this germ theory idea was actually really groundbreaking for its time. That's why he's also sometimes referred to as the father of germ theory, even though a lot of people at the time, most people probably didn't buy into his ideas. And in fact, the city government put this Broad Street pump handle right back after the cholera epidemic subsided. They publicly rejected his germ hypothesis, in part because they thought it would be too upsetting for people to hear about this oral fecal transmission of cholera. It just wasn't the kind of thing people talked about back then. But still, great example of a natural experiment. All right, so this is the end of our discussion on experimental design. No matter whether researchers are using an experimental design or a quasi-experimental design, we have to remember the goal of all experimental research is convergent validity, and that is the ability of different experimenters using different paradigms to find consistent results. And that's how hypothesis testing works, right? That's how you end up building a theory. So in our example of whether trichloroethylene causes leukemia at particular dosage levels, right? What you're going to want to see, I mean, maybe you might start with clinical case reports saying, look, I have all these leukemia patients that I know were exposed to trichloroethylene. You'd want to see experimental results done in toxicology, right? Maybe in vitro studies just on cells in petri dishes. Maybe you'd want to see some animal studies exposing animals to trichloroethylene at different dosage levels. And then ideally you'd want to have what the, gold standard is in human toxics research, which is epidemiology, where you have some people who were exposed to trichloroethylene and following them to see if they develop leukemia at a higher rate than populations not exposed or members of the population not exposed. Okay, but so what you'd be looking for there to have more confidence in your hypothesis about trichloroethylene causing leukemia at a particular dosage level is convergent validity in all of these experimental types. Okay, that's the end of video lecture 8.75.